Professor. So, this is my second recording on the second collab of this assignment. That is the ColabB, where we will write a collab PyTorch from scratch for a three-layer deep neural network for nonlinear regression from scratch without using the PyTorch built-in layer function. So, let's see how we'll do it. I'll just quickly go to the ColabB. So, we will start by setting up our environment with numpy and just so we'll divide this collab into four parts. The first part will be the setup and data preparation. Second will be the manual architecture and logic. Third part will be the manual training loop, and the fourth part will be the evaluation and result part. So in the first part in this notebook, we are building a three-layer neural network from ground by using PyTorch tensors only. We will start by importing PyTorch, NumPy, Matplotlib and setting random seed to 42. This ensures that every tensor we initialize and every gradient we calculate is reproducible. In the second cell, we will generate our synthetic dataset while we are using a complex three variable nonlinear equation involving sines, cosines, square terms. Notice that after generating a data in the numpy, we immediately convert it into a PyTorch tensors, and this is the first step in moving our math to a framework that can handle automatic differentiations. So here we are converting those to PyTorch tensors, and this is our nonlinear output function. In the next cell, we will see the deep learning works best when data is on a similar scale. Here we will calculate the mean and the standard deviation of both our inputs and outputs to perform a z-score normalization. This prevents any one feature from dominating and the gradient and helps model to converge much faster. So that's why we are using the z-score normalization method, and we will normalize it. Once that is done, we will move to the second part of our logic, that is manual and architecture logic. Now we will define our network architecture. We have three inputs, two hidden layer with 10 and 8 neurons. So we have three input layer with 10 and 8 neurons and one output. Because we aren't using nn.linear, we manually initialize our weight matrices w and the bias vectors b with small random values. Crucially, we set the requires grad equals to true. So we are on all of these tensors. Basically, this tells PyTorch to track every operation performed on them, so it can calculate gradients later. So that's why we are defining it true. In the fifth cell, instead of using torch nn.relu, we write our own activation functions. We define the relu and 10h using torch.10h. These non-linearities are what allow the network to learn from complex curve of our dataset rather than just a simple line. So once that is done, we will do the forward pass where the actual prediction happens. We will implement pure three-layer chain, a matrix multiplication of inputs and weights, then matrix multiplication of inputs and weights, then adding the biases, and then applying our activation function. So that we will apply our activation function, and then we repeat this through the hidden layers until we reach the final layer. So first we will multiply the weights and biases, and then we will apply our activation function. In the second layer we will again multiply weights and biases, and then we will weights and add the biases, and then we will again apply the activation function until we reach our final output layer. So this is what we are doing here. Once that is done, to measure how we are doing, we define our loss function. We are using mean squared error, which we calculate manually by squaring the difference between our predictions and the normalized target by taking the average. Our initial loss starts around 1.0. See, this is our initial loss starting at 1.0. Now, At the next cell, our next step starts. The third part, that is the manual training loop. This is the heart of the notebook. The manual training loop for 5000 epochs. We perform the forward pass, compute the loss, and then we will call loss dot backward. This is the PyTorch autograd in action, calculating the gradient for every weight and bias. Finally, we will perform manual gradient descent. We update the weights by subtracting the we will update the weights by subtracting the gradient times of our learning rates inside torch.nograd, and to block to avoid tracking the update itself, and we then zero the gradients and repeat. So we'll zero the gradients and then we will repeat the cycle. By the end of our loss drops significantly from 1.0 to approximately 0.052. So we can see in starting our initial loss here was 1.0, and after the training cycles we can see the final loss is reduced to 0.05 from 1.0 to 0.05. That is almost 100%. So once that is done, we'll enter to the next part of our assignment of the same collab, that is the evaluation and the results. So let's visualize the training. This is the loss curve, shows a classic exponential decay. The initial rapid drop represent the model finding the general trend, while the slower tail shows its fine tuning the weight of the weight's precision. We have achieved a massive 94.7 reduction in the loss. Now we will evaluate the model on the original scale. We calculate the R square, which tells us how much variance in our data model explains, and we have achieved a score of 0.9471, which is excellent. Looking at the first 10 prediction versus the actual values, we can see errors are remarkably small. So this is our predicted values, this is our actual, and this are the errors. The scatter plot compares the prediction versus actual values. The closer the blue points are the red dashed lines, the more actual model. Since main points are tightly closed around the line, we can be confident in model's predictive power. So to conclude the assignment, we have successfully built a three layer neural network with no high level abstraction. We manually handled the weight initialization and then activation functions and then the gradient descent updates using PyTorch only for its efficient tensor math and autograd capabilities. This primitive approach provides the deepest possible understanding how deep learning actually works. So thank you. I'll we will see the next collab in the next video.